Hi, my name is Ronan. This is my video presentation for my 447 final project. Um, I've designed a controller and modeled the plant for what is basically just a camera gimbal with really overpowered motors. This is for a project that involves tracking a fixed-wing UAV mid-flight and sort of like shooting a charging cable at it so that UAVs can perform like autonomous missions for longer without human interaction. Um, so I have these big gear, high gear ratio DC motors, as in they're geared down a lot for high torque, with these Hall effect encoders built in. They don't have any closed loop control. They're not like servos or stepper motors. They're just basic DC motors. Um, and those will be rotating on two axes, this little USB camera. That will just be tracking an IR LED. Um, Without getting into the implementation details too much, it will just use OpenCV to like track the centroid of that bright spot. And since the camera is distortionless, the like deviation of that centroid within the camera's field of view maps linearly to um, the angular deviation between the gimbal and the target. Um, and I'll talk more about my camera plant later. But um, as you may notice, this is like a cascaded control design. So I have two control loops for each axis. This is the altitude. This is the azimuth. Um, they're both being driven by one input, which physically doesn't really make sense unless the target was like only moving diagonally. But since they can be modeled independently, it's just convenient. Um, so there's one control loop just for angular velocity of the motor. Um, so this is just a second order transfer function that models that angular velocity over voltage. Going into that is this very abstracted abstraction of a motor driver, um, which I've just modeled as a voltage clipper. Um, this is important not just to protect the motors, but to model the actual system. The drivers will only be supplied with 12 volts. So if there's like a big deviation from the set point, a big error, and the P term on this controller wants to give the motors like 40 volts, um, the driver is just going to clip that at 12 volts. So until that comes below 12 volts, it'll just be a constant 12-volt voltage. So that's just a saturation block set at 12 and negative 12 volts. So I'll just show how this works in isolation. You'll notice that despite these axes, they should be modeled basically identically. Um, this bottom one I've been using to do more in-depth modeling with like the encoder model and different disturbances. Since they're basically the same thing, I really have only been experimenting with one. The only thing that's different is the inertia, um, which doesn't actually change the behavior that much. But I've disconnected this top one from the uh, angle position controller just to show how it works in isolation. Um, it's a bit zoomed out, but you can see its response is really fast. There's no overshoot. The settle time is quick. Um, this is expected. It's like a DC motor with like very little inertial load, a lot of torque. You would hope it could change its velocity pretty quickly. So that was an easy controller to tune. Um, so that velocity output goes into this integrator, um, which is run in parallel with the inertia model. I should mention, actually, I'll go down to this more in-depth modeled axes. Again, both axes are the same. This one's just simplified for demonstration purposes. Um, this one has the encoder noise modeled. So I've abstracted basically everything away about the encoder except for sensor noise. which could be like a real concern given these motors will actually be running pretty close to each other. And since these are Hall effect and sensors, you could get um, you could get some weird cross coupling or whatever noise from other electrical components going on. So this is just a variable gain on this random noise. Um, that is basically just a dial I can turn up to see like if that noise is really bad, like um, how much does it affect the output. Um, so yeah, that's the velocity output. It gets integrated. It's in parallel with the inertia. That final position output goes through the camera feedback. Um, Inside the camera, I've abstracted basically everything away about an actual camera. Again, it's just some sensor noise. So that's like the culmination of like actual noise from the camera sensor, summed with like the centroid and the OpenCV algorithm kind of blipping around a bit given limited resolution of the camera. It's just sort of a generalized, again, like a knob I can turn to see like if the OpenCV output is really noisy and kind of discontinuous, like how does that affect the overall output? And then the other big limitation that needs to be modeled in the camera plant is its frame rate. Um, Everything else in this system is pretty continuous. I mean, obviously implementing this on like a dev board, like everything would be discrete, but the camera is really what limitates the rate um, of the position controller. Since it's only 120 FPS, I've modeled that with a zero order hold. It's at 120 FPS going into this first order hold just to smooth things out a bit. And that's identical for both axes. I have the feedback from both axes going into this one like camera. Um, yeah, I think that covers pretty much everything. I'll just show how the final position output looks. This is for a 1 radian step change, which is actually pretty big. Like it's unlikely that something's just going to teleport like 1 radian, although it could appear that way given limited frame rate. Um, but since the system is designed to track like continuous movement, like small deviations of continuous movement really precisely, like if you imagine a UAV flying in the air like 20 meters away, it's not going to be like it's pretty continuous. So I want like a big P term to close up those little tiny deviations with like really good response. But that means for like a big step change, you're going to get a bit of overshoot. So that's like a chosen design trade-off. Still, it looks really good though. It's in like a tenth of a second. It gets up there and then settles down in another tenth of a second. Pretty happy with that. And yeah, I think that covers everything. I don't know if I already mentioned both of these systems are connected to one input, which doesn't make sense in real life, but they're independent, so it's just convenient to do it that way. Um, yeah, thank you.